Suppose that a delivery company has just unloaded a 500 Newton crate full of home exercise equipment in your level driveway. So the weight of the crate is 500 Newtons. You find that to get it started moving toward your garage, you have to pull with the horizontal force of magnitude 230 newtons. So F applied, which means equals 230 newtons just to start. Once the crate breaks loose and starts to move, you can keep it moving at a constant velocity. Constant velocity means once acceleration equals 0, that means let's just put what's given to us, a constant velocity v equals 0 meters per second, which no, I'm sorry, it's not 0, equals constant. It doesn't mean it's 0, which means acceleration is 0 with only 200 Newton force. So F applied equals 200 Newton once it starts moving. So what are the coefficient, right? Coefficients of static and kinetic friction. So we want to find out mu s is question mark and mu k is question mark. We have two situations. The one that the crate just before it starts moving, and the crate that is moving with a constant speed. So that means we have to draw a free body diagram in both cases. First of all, let's identify the forces that act on the crate. So we have the U pulling the crate with the F applied. I'm going to call it F from this point on. And then we have the weight of the crate. And then there is it's on a surface, there is this normal force. And then there is this frictional force going opposite to the direction of applied force. Now, we have two situations. Let's start with the first one. First situation where the crate, let's write free body diagram. For crate. Just before it starts moving. Okay, we start with the x and our coordinate system. Here's the x-axis going positive to the right, and positive y-axis going up. And the crate represented as a particle. And then let's put the forces. We have the weight of the crate downwards, and then we have the normal force upwards. We have applied force, F applied, and then we have because just before it starts moving, so that would be Fs, static friction, but the maximum value because at just that moment that it just breaks loose and starts moving. Okay, so now in this case we have, let's name it first one as a case 1. I'm going to call it this 230 Newton F1, and then 200 Newton as a F2 for the second case when it breaks loose and starts moving. Okay, and then for the situation when it starts moving, we have free body diagram for crate moving at constant speed. So we're going to do again the coordinate system. Going to keep it as positive x going to the right and positive y going upwards. Our particle, and the crate as a particle, and then now we have a little bit smaller applied force. Okay, so that's F2. And then we have a friction. This time is a kinetic friction. Okay, and then the weight of the crate and the normal force. Now, all we need to do, we have to apply Newton's second law for both of the cases. Let's start with the first case. So we're going to write sum of the forces by x equals 0. Sum of the forces by y also equals 0, since the crate is not moving. So on the x-axis we have the first F1 and then minus Fs max equals 0. For the second equation, for the y-axis, we have normal force minus the weight equals 0. Now I can say normal force from the second equation. Normal force equals the weight, and we know that static friction, the maximum value of the static friction, equals mu s times the normal force. So from here I can find the mu s, and the mu s equals Fs max divided by normal force. Okay, and then from the first equation we can find the Fs max equals F1. Okay, so I can now plug in the value of Fs max in here and the value of the normal force in here and find what is the static friction. So we have F1 over then the weight, that equals 230 newtons divided by 500 newtons, and that gives us 0.46 for the static friction. So this would be our first answer. Now to find the kinetic friction, we have to apply Newton's second law as well. Okay, well, let's write sum of the forces by x equals max, which equals 0, because ax equals 0 just because v was constant. Okay, and sum of the forces by y equals just 0 because there is no motion on a y-axis. So let's rewrite this equation with the forces included. I have the F2 minus Fk on the x-axis equals 0. And then on the y-axis, I have a normal force minus the weight, that equals 0 as well. From these equations, I can find Fk equals F2 and the normal force equals the weight. Now from the other hand, I know that Fk equals mu k times the normal force. From here I can find mu k equals Fk divided by the normal force, and that is F2 divided by the weight, which is 200 newtons divided by 500 newtons, and that gives us a value of 0.40. This is what we expected, the kinetic coefficient of kinetic friction to be less than coefficient of static friction. So mu k is less than mu s. There is one little thing that I'd like you to notice, that whenever the crate breaks loose, what happens, velocity changes from 0 to its final constant velocity. In that little moment, there is an acceleration. Okay, so just note that, and we kind of didn't use that part to find the kinetic friction. Okay, thanks for watching. Stay tuned for more.